So to get a better model, we'll consider variational autoencoders. All right. So now we'll step into a deep learning world, and this will be something a little bit more sexy, let's say. So now we will talk about this last row in the table. In the next lectures, we'll discuss the other rows. All right. So now we said that this is the generative process in latent variable models. We have this the log likelihood function. We have this integral there. And the question is how to train such model efficiently, especially when we have nonlinear transformations. Because we said linear transformations are very limiting. And of course, if we want something more expressive, we look for nonlinearity. Right. So let us start with this logarithm of the likelihood function, right? So in the past, we had, on previous slides, we had on this PPCA, we had linear transformation and everything was analytical. Now we will consider a nonlinear transformation. So we will assume that for given z, we get x by applying some, for instance, neural network, all right? And since f could be any nonlinear transformation, so right now Professor Bishop cannot simply give us some trick to calculate this integral. Why? Because now this nonlinearity spoils everything in some sense, right? So we end up with an infinite mixture of Gaussians. If this is Gaussian, right, we are saying this is Gaussian and the marginal over this is Gaussian. This is an infinite mixture of Gaussians. We cannot calculate this integral analytically. However, we can use variational inference, approximate inference. And you can look actually in this Christopher Bishop's book, chapter 10, for general information about variational inference. And here we will use it to somehow approximate this integral, all right? So we start with the logarithm of likelihood function. And first we say, all right, we have this logarithm of integral of p of x given z times p of z. And now we will use a very simple trick. We'll multiply these things with 1. And by 1, I mean that we'll just introduce some new distribution, q of z, and we'll divide it by q of z given x, right? Q of z given x. What is that? This is called variational posterior, okay? What is this variational posterior? We'll see in a second, okay? But think of it as an approximation to the real p of z given x, okay? What we can do next? It turns out that we can use, all right, or maybe a side note, we can also learn a separate x for each, separate q for each x, but it would be too complicated, and we use something that is called amortization. So what does it mean? It means that we have one single model, for instance, one single neural network for all possible x's, and then instead of having one q, so one distribution over q of z for one single x, we just use one model for all possible x's, okay? All right, so what we can use to somehow play with this, because this expression, because still we have log outside of the integral, we can use my favorite inequality, I think. This is Jensen's inequality. That simply tells us that, well, if you have log of expected value of some expression, you can go inside this expected value, or in other words, inside an integral, but then you will have a lower bound, okay? But you know, lower bound is not bad. We make some mistake, but at least we still following the good direction. If we want to maximize the log likelihood function if this is something like we maximize the lower bound. So the better we are, the closer we are to the real solution. So this is good. And by using this inequality, what we gain a lot, because we got this logarithm inside the integral. And so now we have the expected value with respect to q, right? So z sampled from q of z given x, and logarithm of p of x times p of z divided by q, right? And now, because we have this logarithm inside, we can use the property of logarithm, and we can reorganize this expression that gives us evidence lower bound, or simply ELBO, right? In the next slide, we will see a different alternative derivation, and you will see why this is also called evidence lower bound. But of course, we see it already here. This is log of likelihood function, lower bounded by this expression. So this is sometimes in statistics or statistical machine learning, this is called an evidence, okay? Right. Now, we can actually look at it even further, and we see that this is a reconstruction error. It tells us the following: sample z from q of z given x. So this is in some sense, encoding scheme. So how to go from x to z. So for low dimensional, so for high dimensional case, space to low dimensional space, and then go back. So decode it back. Take this low dimensional z and generate high dimensional x and calculate the difference. So this is the reconstruction error. And here we have Kullback-Leibler. So Kullback-Leibler divergence. So in some sense, a difference, but in probability space, in the space of distributions. And this is a difference between this variational posterior and the marginal over z's. And this is what we can even call that will resemble this, because I said already about encoding and decoding. So we can say that this q of z given x, the variational posterior, is our encoder, the conditional distribution is our decoder, and this p of z is a marginal over z's. Sometimes people call it a prior, right? But this is the same thing. So this is the nomenclature that actually together, this is the foundation for variational autoencoder, okay? Of course, this is not true that this equation equals variational autoencoder. These components equal variational autoencoder, right? And this is the objective function for the variational autoencoder, right? And now an alternative derivation is here. So you can, during the first watching, you can skip it and come back to that later, but this is also very useful, insightful to go through this derivation. So what we have here, we start with the log likelihood function. We can calculate integral over q of z given x, right? It's simply equality, because this is, here we don't have z anywhere, so it just simply disappears. So we can do that. Then we can actually apply the base rule, right? To obtain, to re-express it, this p of x. So it results in p of z given x times p of x divided by p of z given x, right? Then we can change again the nominator, and it will give us p of x given z times p of z, right? So now you see that we are getting closer to the previous slide. Then we can multiply everything by 1 again, so by multiplying by the variational posterior. Now we can rearrange a little bit, so we can say, all right, p of x given z stays alone. Then we have p of z divided by q of z given x, and we have q of z given x divided by p of z given x. So we get here. Because everywhere here is multiplication, a product, so we can apply log, and we get log of p of x given z, minus, because we flip the order, let's say. So we change the denominator with the denominator. So we have minus log of q of z given x divided by p of z, plus log of q of z given x divided by p of z given x. If we look at this, so this will give us q expected value with respect to q of z given x of log of q of p of x given z. So this is the reconstruction error. Then we get expected value of this logarithm. So this is nothing else as the definition of the Kullback-Leibler divergence. So we have minus Kullback-Leibler divergence between q of z and p of z, plus Kullback-Leibler between q of z given x and the real posterior p of z given x. Of course, we don't have this, right? We don't have this quantity here. We don't have this distribution. But this is not the point here. The point is that through all this derivation, we have equalities, right? But we notice that we actually have, this is the reconstruction error. This is something that we call the regularization, right? So this is exactly the ELBO, right? And so how we get the lower bound? Well, the Kullback-Leibler, the property of the Kullback-Leibler is that this will be never negative. So it will be always higher or equal 0, right? Equal 0 if these two distributions are the same, okay? So why we even bother, we spend this 5 minutes on deriving this thing? Because this is very insightful. Because it says that if we take variational posterior that is poor, then this lower bound is very loose. It means that this circled quantity, this Kullback-Leibler, tells us how big error we make. How big is the difference between the ELBO and the true log likelihood function, okay? And so now this is very important information, and we will briefly talk about it in this normalizing flows section later on in one of lectures. But please keep it in mind, okay? This is the indication why we need to have possibly as flexible as possible variational posterior to make this gap as small as possible. All right. Right. Okay. So this is the theory. Now we are stepping into the practice. Okay. So we say that the variational posterior and the likelihood function, or simply the conditional distribution, so the encoder and decoder, are parameterized by neural networks. Okay, so we say that we have this q of z given x. It's a neural network that in the end will give us parameters, for instance, of Gaussian distribution. Then we sample something, right? We sample this code, and using a decoder network, a neural network, we will obtain the reconstruction. All right. Another important thing in variational autoencoders is that, of course, we still need to calculate the integral with respect to the variational posterior, q of z given x. In practice, we just simply take we just sample one z, and we calculate gradients with respect to encoder and decoder. However, in order to ensure that the variance of this estimator is not so high, and about it you will also listen at one of other lectures on reinforcement learning. But here, just please believe me, okay? So we can use something that is called the reparametrization trick. And this trick tells us that we can move stochasticity to independent random variables, okay? So what does it mean? It means that when we want to generate z for given x, ideally, we should do it by introducing some new random variable, and this encoder is actually deterministic, and we just generate something stochastic by adding independent auxiliary random variable. And in the case of Gaussian, we can do that, right? So if we take standard Gaussian distribution, so this is this green curve right here, centered around 0 with variance equal 1. We can turn it into any other Gaussian by shifting it, so adding a mean, right? So adding a mean, and then squashing it or making it broader by multiplying by standard deviation, right? And this is the idea of the reparametrization trick. Try to think of some distribution as some transformations and introducing some noise somewhere. So in this case, the encoder gives us the mean value and standard deviation or variance. Then we can take square root and just multiply the standard deviation by independent random variable. Right. Why variational autoencoders are so great? First of all, we have the compression for free because we copy inputs to outputs through a bottleneck. So we go from high dimensional space, we go to low dimensional space. So this encoder creates some kind of code of given data point, and then we go back to the high dimensional space, right? Of course, we can get some blurriness, but more or less you see that, all right, these black dots, these are, by the way, real images of cells. So you see that these cells are in proper places, right? And some other kind of cells, they are also here, indicated by colors. Right, so this is first good thing. We have the compression for free. Second thing is that we have this marginal over latent codes, so we can easily generate, because now we can just pick one point, we can generate one point in the latent space and let it through the decoder, and we get a new sample, again some cells somewhere, right? We can repeat it, we can sample other points, and we get new images. And now this is the general concept, how it works and why VAEs are nice. But now we will talk about a very specific implementation of VAE. We call it vanilla VAE because this is very simple, without any special tricks. So let's say that we have an image X. First, we go through the encoder, and an example architecture could be the following. So we have a linear layer. We're going from d-dimensional space to 300 neurons. Then we apply ReLU. Then we apply another linear layer that we go from 300 to some 2 times m. And why we have 2 times m? Because we need to produce mean values and standard deviations. And at the end, we just split them, the output of the linear layer, into 2 vectors. Okay? So this is how it goes further. So we have applied the reparametrization trick. But remember that mean and standard deviation, these 2 vectors are dependent on x. So this is the amortization. And then we, of course, add some independent noise to generate z again. Please note that we don't have any nonlinearity here at the end, because we model means and log of standard deviations. Why we take log of standard deviations? Remember, standard deviation must be positive. By taking logarithm of a positive number, you will get real value. Okay, so this is a simple trick to make it easy in your code. So just simply use a linear layer, produce some two real valued vectors, and then if you want to get variance back, you need to take exp of this log standard deviation, or sorry, standard deviation back. So we take exp of log standard deviation, right? And then we have a decoder, right? So how this decoder works now? We take this latent code, sampled, right? Sampled, remember, we added some stochasticity, so this is sampled. We take another linear layer. Now this is m-dimensional, right? So we go back to, for instance, 300 neurons. We apply ReLU. Again, we apply another linear layer that go from 300 to D, so the original size of the image, and we predict means. Again, we have no non-linearity at the end because we model real valued, for instance, pixels, right? Right. So this is very exemplary neural network. Here is a little bit of an overstretch because we shouldn't use Gaussian distribution for pixels, but for sake of simplicity, we keep it like that, okay? So yes, so how this translates to math? So we just in this example we just use Gaussian distribution for the decoder with assumed variance equal 1, okay? And then the neural network returns only means, right? For the variational posterior, we take Gaussian again, and for the marginal over this, we take standard Gaussian. We approximate the expected values with respect to the variational posterior using one simple sample, right? So this will result in this objective, okay? This is again the reconstruction error. This is the approximated reconstruction error and the approximated Kullback-Leibler term. As I said, we assume Gaussian variational posterior, we assume a standard Gaussian prior. Again, I want to highlight it, and as strong as I can, we cannot pick any arbitrary distribution for our observed variables. We must be very reasonable about it, and we must be sensible, and we should pick something that is appropriate for our data. If our data is real valued, we can take, for instance, Gaussian, we can take Laplace, we can take Cauchy, right? Some distribution that has a proper, is defined over a proper support, so proper values, okay? If you want to model binary variables, something that takes 0 or 1, you cannot use Gaussian. You must use Bernoulli in this case, right? And so on, so on. So if you first always please think about your data. What is your data? What kind of values your data can take? And then you can think of a proper distribution for that. This is the prescribed latent variables models. We must be correct with taking proper distributions. In many papers, even some accepted papers to some world-renowned these conferences, people still use wrong distributions. They say, well, we can do that. Of course, you can do that, but this is not correct. Okay, be correct. All right. So this is the vanilla VAE, and now also a little bit of a code. I will not go into details. I just want to highlight that this corresponds exactly to previous slides. So I hope that you can slowly go through that and you can think of this implementation. I just want to highlight that the reparametrization trick is very simple, right? So we take mean and log standard deviation. With this log standard deviation, we turn into, oh, there is a mistake. It should be log standard deviation, not variance, sorry. But to obtain standard deviation, we just take exp of log standard deviation. Then we just generate from standard Gaussian. This is, by the way, PyTorch code, right? And we get this z. This z should be also small. And this encoder returns, remember, two times larger output because we need to model means and standard deviations. Okay. And the forward code is very simple. So we encode our inputs once, then we apply ReLU, then we encode it using the second linear layer, and we can view it in such a way that we have this, one dimension for means and one for variances in this tensor. Then we can simply slice them into two vectors. And for this, it's again log standard deviation, sorry, my bad. And then, of course, we can apply reparametrization trick, and we can decode it back. And this forward will give us the decoded values, mu and log standard deviation. Why we need all of this? Because we will use them in the ELBO, right? So first we need to calculate the reconstruction error, and for this purpose we used mean squared error, because remember, we assume that the Gaussian has standard deviation equal 1, so we can use it here. And Kullback library is just difference between log normal for the variational posterior minus log normal for the prior. Of course, here we assume that somewhere before we have this log normal implemented properly. And remember that in PyTorch we assume that we minimize an objective function. So since we maximize the ELBO, we need to take the negative sign, right? We take the negative value of the ELBO to have the minimization problem. So what are common issues with VAEs? So first of all, we have weak decoders. So if we have weak decoders, we get bad generations, reconstructions. If we have weak encoders, remember, so there was this gap, right? So weak variational posteriors will have bad latent representation, so-called something that is called posterior collapse. So it means that variational posterior will be too similar to the prior. And also, what was in the very beginning of variational autoencoders somehow skipped is that actually it is not advisable to use fixed prior or this marginal over z's. We should have learnable priors, because otherwise we can get very bad generations. And of course, the good and very important question is, if we think of variational posteriors, what kind of family of distributions we should use, right? We will see that actually in the other lecture, that we can use something more flexible. Here are these components written in one slide. So just to give you some, throw at you some ideas what we can use if you decide to work on this assignment 5A, so VAEs and GANs. So this is what you can look for, or maybe afterwards, if you're interested in writing a master thesis, just hit on me and we will think about some interesting topic. So for decoders, we should actually use some rest nets, dense nets, or some other fancy stuff like autoregressive models and so on. If we think about variational posteriors, so again, we should we can mirror the architecture, so we can use ResNet, DenseNet, but we can also use normalizing flows. Back in the day with my students at UVA, I worked with hyperspherical distributions, so not Gaussians. In a follow-up paper, I think from DeepMind or somewhere from the UK, so they proposed hyperbolic, maybe Oxford, yes, I think they proposed hyperbolic normal distribution. So again, something different than Gaussian. We don't need to stick to Gaussians as long as it makes sense. We can use group theory, whatever fancy thing you can think of to propose some more powerful variational posteriors. And last but not least, we should look into marginals. I believe that we should make them learnable. And for this purpose, you can use autoregressive models. We'll talk about them during next lecture or one of next lectures. But you can use these ideas not only to model the pixel space, but also the latent space in VAEs. You can use normalizing flows. You can use something that together with Max Venning we proposed 2 years ago, Venn prior, or you can use some implicit priors. So GAN-like ideas to model this P of Z to improve generative capabilities of VAEs. Or you can even think of some different objectives. So you can change this objective. You can use adversarial learning, so ideas from GANs, or some maybe other probability metrics. You can replace reconstruction error with MMD, or you can do something else that will result in a paper that is called Wasserstein Auto-Encoder. Again, this slide is super heavy. So this is rather for you to see that there is a plethora of different directions, and this is extremely interesting field. Okay, so I hope that this attracts your attention, and maybe we can work on that in the future. But yeah, this is something that there's a lot of things that could be done. And at the end, I want to mention something that briefly mention something that nowadays gets a lot of attention. So this is hierarchical VAEs. So instead of having one single Z, we can think of a hierarchy of Zs. And here are two examples of papers. On the left, a paper together with my great master student that defended this year, Yannis Gatopoulos. So we used hierarchical VAE with some extra tricks. I don't go into details here. It's more like to see that you can use a hierarchical VAE and you can get better results. Or a very recent paper from NVIDIA group that they used again some fancy architecture of VAE, but again it was very crucial to have a hierarchical model to generate very nice pictures, and I want to share with you these pictures. So first, from our paper, you can see some generated low 64 and 64 faces. So this is our model. Again, I don't go into details, but this is our model and this is our model in the middle. So all these faces are in some sense fake. So they are not in the training data. Maybe this fellow looks a little bit like Matthew McConaughey, or what the name of this actor is, but still it's a little bit different. And on the right is, let's say, a boosted VAE, not vanilla VAE, but you see that actually these faces look also not so bad. And from NVIDIA, of course, they have way more resources than we do in academia, unfortunately. And they were able to train VAEs on much larger images, 256 times 256 pixels. And these are generated faces, okay? What does it mean? It means that none of these people is real. They are fake. There is not such person. It's generated by a generative model. And what I would like to to indicate in this is that take a look at details, right? So for instance, you can say that this lady looks like very smooth, like really an actress or a model, right? But take a look at this fellow. This guy, he has wrinkles. Teeth are something like very real, right? Eyes are very consistent. All these details, it's incredible. It is incredible. Look at this lady and this uh, earring, right? So this is again something like fancy, right? But it's totally fake. It's synthetic, right? Or this person, he has beard, all these details. This is so consistent, right? It's incredible. Of course, maybe you can spot some weird things like this lady, this earring is, where is the hole? Maybe here, but to me it's amazing, right? And of course it was possible because this was NVIDIA. They had a lot of resources, but this is important to indicate, to show, right? Showcase that this is possible to generate something that could maybe pass this, I know, image Turing test. It's impossible to say whether this is a real photo or generated by a model. All right. So what are advantages and disadvantages of variational autoencoders? So definitely, this is a nonlinear model. So it has a lot of modeling capabilities, right? As you saw on the previous slide, it could generate amazing stuff. The training is rather stable. It allows compression. It allows to generate things. And we can actually pretty well approximate the likelihood function, or the log likelihood function. So this is good, right? So keeping this picture from the first slides about these horses and cats, so we can calculate, approximate at least this p of x. So we can use it for some kind of reasoning. What are disadvantages? Well, we don't have analytical solutions, but of course I put it just to be aware of that, but I would say, who cares, right? As long as we can approximate things well and we can do crazy stuff with that, it's fine. We don't have exact likelihood. Well, this might be an issue because you can say, I still need to approximate the log likelihood. I don't have the exact values, so maybe I'm making a big mistake. I don't know, right? There is this, so this is directly connected with this potential mismatch between true posterior and variational posterior. Well, we don't know what is the mismatch, so we should try our best to make it as flexible as possible. And one of the biggest disadvantages of VAEs were that they generated blurry images. But ladies and gentlemen, not anymore. This year, really something like a couple of months ago, people showed from NVIDIA that this is not true. We can really generate beautiful images. And this is the end of this lecture. I hope that you enjoyed it. It's really fascinating topic. There is a bit of math, a little bit of, maybe some derivations that are not so easy to follow. Please, after watching this, please try to go through slides again. Take a pen, maybe try to do it by yourself. If you find some problems, please write a comment in the discussion board on Canvas. And I hope that you will see the beauty of VAEs, because this is, and this kind of generative models, because this gives us a lot of opportunities. This could be combined as a probabilistic model. It could be combined with any other probabilistic model. So what we showed in this first slide, you can just train a classifier, you can train this generative model P of X, you can combine them together, you can do great stuff in reinforcement learning, active learning, and so on. All right, thank you very much. And if you have any questions, just leave them on discussion board on Canvas. Thank you very much.